Hello, AP Calculus. Welcome back. How did the quiz go? How was the quiz? Hopefully it wasn't too tough. Open notes. Remember, all the quizzes are going to be open notes. All right, so that'll get home to me, and I will grade that and enter it from home, just like all the homework and everything else. But for today, we're going to continue now. We're going to talk about another type of differentiation, something called implicit differentiation. Implicit differentiation versus explicit. What we've been doing up till now has been explicit differentiation. Let me explain the difference. When we have a function, some function in the form f of x equals something, this is y equals, and it's a function, y equals f of x, that's explicit, and we have some sort of function over here. But implicit is an equation. I want you to think about an equation that describes some sort of relationship. For example, probably the quickest and easiest one that we can relate to is the equation of a circle. Something like x squared plus y squared equals 4. We know that this is a circle. The center's at the origin. The radius is 2. If I graph this, center at the origin, radius 2. Well, that's not too bad. I get a circle. And I cannot explicitly define this. It's not a function. I suppose I could subtract x squared, take the square root, and I could have y equals the positive square root of 4 minus x squared, and y equals the negative square root of 4 minus x squared. In effect, I'll have the top and the bottom, and then I could find the equation of tangent lines. So for example, if I wanted to find the equation of some tangent line at some point, when x is equal to 1, now notice, when x equals 1, the function is defined here and here. So I'm going to have a tangent line up here and a tangent line down there. Clearly they are not the same slopes. So I'm going to get two different tangent lines. I'm going to get two different slopes here. One of them is a positive, the other is a negative. Would they be perpendicular? Not necessarily. And a lot of times it just depends on the curve. But clearly there is a tangent line here, and we can find the equation of the tangent line. But how would we take the derivative of this? Well, this is where implicit differentiation comes in. So we're going to find dy dx. So I'm going to be a little bit specific here, and we want to find dy dx. Find the derivative, dy dx. So I'm going to take the derivative with respect to this. So I'm going to have the derivative of the equation x squared plus y squared equals 4. Now, follow as I take each step along the way. We can use the property of the derivative of the sum is the sum of the derivatives, which means I've got the derivative of x squared plus the derivative of y squared equals the derivative of 4. And let's break these down one at a time. The derivative of x squared, well, we know that. That's just nice, well-behaved 2x plus, let me talk about this in a moment. What's happening over here? The derivative of a constant, well, that's 0. So what's going on over here? I want to take the derivative with respect to x of y squared. Well, the derivative of y squared is going to be 2y, but I'm going to have dy dx left over. Over here I did as well. I had 2x times dx dx, which is just 1. So we don't even put it there anymore. But now I'm going to have 2y dy dx when I take the derivative of y squared. I'm still going to have the dy dx over. That's going to be my derivative. What are we trying to find? Dy dx. We're trying to find the derivative. So I'm going to take this equation and solve it for dy dx. Subtract 2 x's from both sides. Divide by 2y. And dy dx is negative 2x over positive 2y. The 2's are going to cancel. And I get negative x over y. That's my derivative. That's the derivative of the circle. So, and remember, the derivative is the slope of the tangent lines. So if I wanted to find, if we go back up here to our circle, if I wanted to find the equation of this tangent line right here, where x is equal to 1, the slope is going to be, plug in 1, I need the y value, because this is a different y value from that one. So to find the y value, I'd have to plug it in here. 1 squared is 1, minus, I'd get the square root of 3. So the slope of this tangent line would be negative 1 over root 3. The slope of this one would be negative 1 over negative root 3. So the two tangent lines would be 1 over root 3 and negative 1 over root 3, which are not perpendicular. They're not negative reciprocals of each other. And then, of course, we know the coordinates of the point. We can find the we know the slope of the tangent line, and we can find the equation of the tangent there. So we use implicit differentiation when we have an equation that we cannot solve explicitly for y. Let's take a look at some more examples. So in the next example, I'm going to have some curve x plus the square root of y equals 1. Now, this one I could actually solve, subtract x and then square both sides, and I could think about this as y equals 1 plus x squared, or actually 1 minus x squared, wouldn't it? Because I square both sides. But I don't want to think about this here. I want to think about this. I'd have a positive and a negative side over here. What would this function actually look like? Well, if I want to find the derivative of this function, I want to find d dx of the function. So the derivative with respect to x of, oh, I said function, didn't I? It's not a function. It's not a function at all of this equation. So break it down. So I would have the derivative with respect to x of x plus the derivative with respect to x of the square root of y equals the derivative with respect to x of 1. The derivative of x is just going to be 1. The derivative of the square root of y. Now think about this as y to the 1/2 power. So it's going to be negative 1/2 times y to the negative 1/2 times dy dx equals, and the derivative of a constant is 0. So now I need to solve this for dy dx. Subtract 1 from both sides, negative 1/2 times, and I'm going to write this as 1 over the square root of y, dy dx equals negative 1. Multiply both sides by a negative, multiply both sides by 2. 1 over the square root of y, dy dx equals positive 2, and then multiply both sides by the square root of y. So my dy dx, the derivative of this equation, is 2 times the square root of y. And I could use that to find the equation of the tangent lines anywhere. All right, let's take a look at another one. Remember, when we take derivatives, we are differentiating with respect to x. So a little bit more confusing, a little bit more going on here. X squared y cubed equals 2x plus 1. And I want to take the derivative of this. Now this would be very difficult to try to solve for y. I don't think I could use my whole plus square root and minus square root thing going on, because it's a cubic. So I don't think I've got any other options here, any other way of writing this. I'm going to have to differentiate this explicitly. And not only that, I'm going to have a product here. This is going to be a product rule. All right, so again, I want to break it down and write every step along the way. So I'm going to take the derivative with respect to x of this side, x squared y cubed, equals the derivative with respect to x of that side, 2x plus 1. And I've got a product rule here. Remember what you say when you've got the product rule. It's the first times the derivative of the second plus the second times the derivative of the first. So here we go. First, x squared times the derivative of the second. The derivative of y cubed is going to be 3y squared dy dx. plus the second y cubed times the derivative of the first, 2x, equals the derivative of 2x plus 1 is just going to be 2. All right, let's clean this up here a little bit. I'm going to have 3x squared y squared dy dx plus 2x y cubed equals 2. I want to get the dy dx alone by itself. I want to solve for the dy dx. So subtract this from both sides. 3x squared y squared equals 2 minus 2xy cubed. Oh, I forgot the dy dx in here. Oh, that's very important. This is the whole thing we're solving for. This is what we're trying to solve for here. So I need to have my dy dx here. And now I'm going to divide both sides by this, and I get dy dx equals 2 minus 2xy cubed over 3x squared y squared. And now if I know a point, for example, if I wanted to find the slope of the tangent line at the point where x is equal to 1, I would plug in x equals 1 here. I need to know the corresponding y value. So after I plug in x equals 1, I'd have to solve for y. I might have 1 corresponding y value, or 2 corresponding y values, or even, I suppose, 3 corresponding y values. So implicit differentiation. Let's take a look at another example. Let's take a look at the equation 3x squared minus 5xy plus y squared equals 10. Now notice, we're not talking about what would these things look like graphically. I mean, what would this look like? A lot of these things are sideways parabolas or some sort of sideways relation, looking like one of our polynomials but sideways, and all sorts of crazy, strange things. We could graph it parametrically. We could graph this a couple of different ways here. But really it's all about the derivative and finding the equation of the tangent line. So I want to find the derivative of this function right here. Notice I cannot solve it for y. This would be very difficult to solve for y. And I'm going to have to differentiate it implicitly. And I do have a product rule there. But remember, you can factor out the negative 5 to do the product here. All right, see if you can stay ahead of me on this one. So I'm going to take the derivative with respect to x of the 3x squared minus 5 times the derivative with respect to x of the xy. Well, I factored the negative 5 out. I probably could have factored the 3 out here as well. Plus the derivative with respect to x of the y squared equals the derivative with respect to x of 10. So this one's pretty easy to do. 2 times 3, 6x minus 5 times, here comes my product rule, the first times the derivative of the second, dy dx, plus the second, y, times the derivative of the first, 1. Plus the derivative of y squared is going to be 2y dy dx equals, and the derivative of a constant is 0. If I clean this up here a little bit, notice I've got 2 different dy dx's. How are we going to isolate those? 6x minus 5x dy dx minus 5y plus 2y dy dx equals 0. And I want to isolate, I want to solve for the dy dx's. I want to get those alone by themselves. All right, so I've got 2 terms that have got the dy dx's in them and 2 terms that don't. First, I'm going to get rid of these. I'm going to add 5y and subtract 6x to both sides. And I will have negative 5x dy dx plus 2y dy dx equals 5y minus 6x. Now I'm going to, so I've got all the terms that have got dy dx on one side, everything else on the other side. Factor out the dy dx. dy dx times, and I've got negative 5x plus 2y equals 5y minus 6x. And then as you can imagine, I'm going to divide both sides by this. So my final answer, dy dx, the derivative of this equation is 5y minus 6x over And if I write this positive term first and then the negative term, 2y minus 5x. So there it is, implicit differentiation. Now let's take a look at an example where we'll actually keep going and we will find the equation of the tangent line. So we'll be plugging numbers in at the very end and talking about what the equation of the tangent line is. So a little bit more involved in this next example. So I want to find the equation of the tangent line to the curve defined by x squared plus 2xy minus y squared equals 1 at x equals 5. All right, so what are we going to need to do here? A couple of different things. I know at some point I'm going to have to take the derivative of this thing. But at x equals 5, well, what's the y value? So let's take a closer look at x equals 5. If I plug 5 into my equation, to the original function, I've got 5 squared plus 2 times 5 times y minus y squared equals 1. 25 plus 10y minus y squared equals 1. Add the y squared to both sides. Subtract the 10y to both sides. Subtract 25 from both sides. Solving for y. This is nice and well behaved and factorable. Y and y. Two things that multiply together to give me negative 24 and add up to give me negative 10. How about negative 12 and positive 2? So I get y equals 12 and y equals negative 2. So I've got two different points. X equals 5 is twice on this curve. I've got the point 5, 12 and the point 5, negative 2. So which point do I want? Which tangent line do I want? Well, we could go ahead and find both of them. Once we've got the derivative, that would be easy. But for the sake of this example, I'm only going to find the slope of the tangent line at this point right here. So I've got my point. Now I need the slope of the tangent line. And in order to do that, I have to find the derivative of this curve. So now the second part of this problem, find the derivative. We're going to find it implicitly. So my curve is x squared plus 2xy minus y squared equals 1. Take the derivative here, the derivative with respect to x of x squared, plus the derivative with respect to x of 2xy, minus the derivative with respect to x of y squared equals the derivative with respect to x of 1. This is going to be 2x times dx, which is just 1, plus here 2 times, I've got a product rule, x times y, first times the derivative of the second, plus the second times the derivative of the first, minus 2y dy dx equals the derivative of the constant is 0. So let's break this up using the same trick as before. Get all the dy dx's on one side, everything else on the other side. Factor out that dy dx and solve. See if you can stay ahead of me on this one. We'll compare our answers at the end. That's what I need to isolate. That's what I'm trying to find, the derivative, dy dx. factoring out. Dividing. There it is. There it is. There's my derivative. There's my nice, well-behaved derivative. Seems like I noticed I could factor a 2 out of the top and a 2 out of the bottom and simplify it here a little bit if I wanted to do that. All right, so now I want to evaluate this. You know what? I think I made a mistake here. Did you catch this mistake? Oh, I'm not going to stop the video and go back again, but take a look at this mistake here. Where did that x come from? I don't think it should be there. I think I accidentally foiled the x out. I don't think that x should be there. Did you catch this mistake? So 2 times y, that should just be 2y. There shouldn't be any x there. Which means there shouldn't be any x here. There shouldn't be any x here. And there shouldn't be any x there. Yep, that was a mistake. Did you catch it? All right, so now I've got my derivative. I've got my correct derivative here. What's the next thing we need to do? Well, now we're going to evaluate it. Remember, we're looking at the point 5, negative 2. So at the point 5, negative 2, the derivative, the slope of the tangent line, would be negative 2 times 5 minus 2 times negative 2 all over 2 times 5 minus 2 times negative 2, negative 10 plus 4 over 10 plus 4, which gives me negative 6 over 14, negative 3/7. So my slope is negative 3/7. The slope is 3/7, and I've got a point. So now I'm going to use the point slope formula. Substituting in y minus the y value, there it is, negative 2 equals the slope, negative 3/7 of x minus the x value at 5. Y plus 2 equals negative 3/7 x. Negative times a negative is a positive. 3 times 5, 15/7. Subtract 2 from both sides, and I get y equals negative 3/7 of x minus 2 is like negative 14/7. So plus 1/7. All right, there it is. There's our final answer. There's the equation of the tangent line. All right, so let's take a look at 2 more examples. The video is getting a little bit long here, but I want to make sure that we do 2 more examples before we move away from this. How about this curve? X squared y equals 1. Find the derivative of this curve. Well, again, it occurs to me that maybe I could write this as a function. If I divide both sides, I could write this as 1 over x squared. And I know the derivative of this. Y equals x to the negative 2. Y equals negative 2x to the negative 3. Y equals negative 2 over x cubed. I know I can do this one explicitly. Well, what if I did this one implicitly? Would I get the same answer? Let's take a look at it. I've got product rule here, so I know it's going to be the derivative, let me write it out, the derivative of x squared y, the derivative of 1. So product rule, the first times the derivative of the second, plus the second times the derivative of the first equals 0. Clean this up here a little bit. X squared times dy dx plus 2xy equals 0. Subtract x squared dy dx equals negative 2xy. Divide both sides. Dy dx equals negative 2xy over x squared. So the derivative is negative 2y over x. Now wait a minute, those don't seem to be the same. These don't seem to be the same. What's going on here? Is one of them right and one of them wrong? No. They're both right. But these don't seem to be the same. Why not? Well, because this one's got y's in it. And what is y really? Well, if I take this equation and solve it, y is really 1 over x squared. So let's simplify. Let's do that substitution here. So dy dx equals negative 2 times 1 over x squared over x. So I'm substituting in now. Where I had this y term here, I'm substituting in 1 over x squared. And then if I simplify this, I get dy dx equals negative 2 over x cubed. And now we can see that really, indeed, they are exactly the same. They're the same. All right, let's try one more to do implicitly. And as you try this one, try to stay ahead of me. Try to get this one done before I get it. X cubed minus xy plus y squared equals 4. All right, let me pause for a minute, see what you can do with this one. Did you catch the little product rule going on in here? All right, let's see. 3x squared minus and I wrote it so the positive term would be first. And I suppose technically we would want to have the negative 3x squared, negative 3x squared plus y over negative x plus 2y. That looks a little bit awkward, but that's probably the better format, the better way to have it. All right, implicit differentiation. There it is. We'll be back in a minute for another video, and we'll talk some more about implicit differentiation, do some more examples.